function, simply to produce salt. Each pond has a slightly different salinity, hosting either algae or tiny animals such as brine shrimp. Recently, a group of partners, including conservation organizations, the state of California, and the federal government, have purchased 10,000 acres of salt ponds in the North Bay and 15,000 acres in the South Bay. The goal is to restore these areas for natural processes to take hold. What has been a closed system for salt production will be reshaped with plants and animals in mind.
About 80% of the tidal marshes in San Francisco Bay have been lost. They were lost to fill, they were lost to diking off for farmlands. They were made into salt ponds. The salt ponds that are ringing San Francisco Bay now, those ponds are between 50 to 150 years old and have been used to make salt. They represent this great opportunity now that they are in public ownership to become the restoration template for San Francisco Bay.
Alright, so this is day 3 and we're at Hong Kong Park. It's beautiful here, other than the fact that it's like 33 degrees outside. And Say is right beside me doing his stuff.
I got 28 new messages. Yeah.
And he's on his laptop on Facebook uploading
It's got a new one.
pictures and comments. Yeah, there's Wi-Fi in parks. It's awesome, eh? So yeah, anyway, later on we're gonna move down there, and then Victoria Peak is way up there. We're gonna take the tram, show you more pictures afterwards. Alright.
It's really a great example of integrated science and what USGS can bring to bear with biology, hydrology, and geology. We're mapping, we're measuring, we're modeling, we're observing systematically the birds, the fish, the invertebrates. So we have a lot of different scientists coming to bear on these questions of how to restore these wetlands.
The initial purchase and restoration of salt ponds in the North Bay in 1994 has formed a sort of testing ground for guiding present work in the South Bay.
We have learned a lot from working in the North Bay salt ponds about how changing the ponds may alter their ecology. So we're learning about how, if you open levees, how the differences in the pond bottoms and how the pond may fill up and become vegetated will change, and hopefully those experiences will help us learn about what will happen in the South Bay salt ponds as they're restored also.
The way Cargill ran it is it was one big system. So they would never discharge any water back into the sluice. So they would have one intake, it would funnel water all the way through these salt ponds, and then as the salinity would get higher and higher basically into their concentrator ponds where they would extract the salt from it. So what we did is we broke it up into several smaller systems with all these intakes and discharges to funnel fresher water through. And what we found is that the shorebird and waterfall numbers have been increased by 100%. Already, 120% in some ponds. So you can tell that we're starting to get fish in here. We're starting to get a lot of fish-eating birds in here. So basically before that there was only a few species that ate the brines, brine shrimp and brine flies.
We're also looking at the California clapper, which is an endangered species and only found in the Bay Area, primarily because the habitats that were lost, the tidal marshes, are its home. And what we're trying to do is look at how the recovery of these habitats may actually improve the populations of this species.
The California clapper rail rarely flies. It forages for things like clams, snails, sometimes dead fish, and even mice. They scour tidal flats and very shallow water, always with plants nearby for cover. The tidal marsh it calls home is one of the primary habitats being added back by the restoration. Illustrated graphically here, the process of creating tidal marsh depends on the tides carrying in huge volumes of sediment to form a foundation where the marsh can develop and thrive.
Right now, I'm beyond my knees in mud. I'm in a side channel to Coyote Creek, and the only reason that I'm here and not underwater is because it's at a very low tide. The tide range here is 10 feet or more, and 6 hours ago, if I had been here, I'd be underwater by about 3 or 4 feet. What you see over here is the tidal marsh surface. That's at the level of the highest tides. And the importance of all this is that when the tides come in, they bring sediment, and that is what is going to fill up the salt ponds and bring them up to the desired level, where then they can be colonized by vegetation and turn into tidal marshes and create new tidal marsh habitat.
The team has used airborne surveys called LiDAR, sonar from boats, and sediment sampling to show where sediment is in the bay and how it moves around. The data are combined to form models that are used to forecast the outcomes of various changes to the system. The models are refined as the restoration moves forward.
Another bit of uncertainty is what's going to happen with climate change, with, in particular, global sea level rise. Is there going to be too much stress on the system? Is the demand for sediment? Because when you raise the water, what has to happen for restoration to be successful is you have to put in enough sediment to keep up with the rise in the water. And so that's a big question. It's tremendous volumes of sediment. Just for the tidal flats alone, it could be on the order of 50 million cubic meters. That's about 50 superdomes in New Orleans filled of sediment. Just an incredible amount of sediment.
Water-moving sediment is the key to this process. Throughout the bay and salt ponds, water's role is varied and dominant. The life struggling to survive here depends in many ways on the water quality, and the tidal forces at work. The existence of gates to raise and lower water levels in the ponds adds an unusual ability to control water flow of the overall system. Here, the scientists are collecting data on just how much water is passing through the gates from the pond into South San Francisco Bay.
To do this, we used an acoustic Doppler current profiler, which is a long name for a small instrument.
It is measuring velocity or speed of the water and at the same time tracking the bottom. By towing the device back and forth in front of the discharge pipes, they can calculate how much water is passing through. This information has been crucial for developing the model that is used to determine how much water is likely to pass between the ponds and the bay.
The managers of these ponds need to know the volume of water entering South San Francisco Bay so that if there's anything in the water in the ponds, they can calculate how much of that is actually entering San Francisco Bay, whether it's a lack of oxygen in the water or if it's phytoplankton or perhaps mercury or anything else that they might be interested in.
Water enters and leaves the system through daily tides. Fresh water passes down the surrounding landscape through creeks, which become sloughs and wind out into the bay.
Stream from here is the New Almaden mercury mine, which was at one point, I believe, the largest mercury mine in North America. And the mine tailings from that and put quite a bit of mercury into these soils and into these sediments out in these sloughs.
Here, samples are being collected for water quality and sediment load. Regular sampling of this type is taking place in all of the sloughs entering the South Bay.
PH 4.53, come down a little
This
bit.
work takes place from land or from boats. This way, water samples cover the entire system, from upstream urban areas through the intertidal zone,
pH 7.36,
all the way into the bay.
DO is 5.68.
Details of exactly what is traveling in the slough water and how much water is flowing are the kinds of data that help build the models of the overall system.
And so one of the things we've done is develop a numerical model of the Alviso salt ponds that we see here that looks at the water level, salinity, water temperature of the ponds, so that the resource managers can use that model to manage the ponds to provide the optimal habitat for migrating birds. So that we may have fewer ponds, but they'll actually be managed for waterfowl and not for salinity.
Well, we have both terrestrial marsh birds, but also a lot of migratory birds that come through in the winter and through the migration periods. And those birds, a lot of them are shorebirds and waterfowl that use the Bay Area as a stopping point on the way north and south from the breeding grounds. Salt ponds, again, have been here a long time. So salt ponds are part of the environment that have been here over 100 years. So they're not exactly a natural habitat, but they're certainly a long-term habitat. And we just don't understand what will happen if they disappear all at once. So what we're hoping is to have a phased-in approach of change where we can look at what value they have for natural resources, including migratory birds. And as we do change, we'll be able to adjust for the differences as we lose these habitats that have been here quite a long time.
Studies of shorebirds and terns are providing an important window into the overall quality of the salt pond habitat. Mercury washed down from the upstream mine tailings is of particular concern. It is toxic to fish, birds, and humans. Part of the research focuses on reproduction. The scientists set out to determine the health of eggs and the young.
We go out into any of the nesting areas and we take a lot of equipment with us, and when we get across to the islands we walk them very slowly looking for all of the nests.
Egg number 1.
When we come to a nest, we float the egg because there's this little air pocket at top.
The air cell in the egg grows larger as the embryo develops. Based on how the egg floats, the scientists estimate the stage of development of the egg.
And once we've aged all of the eggs and numbered them all, we put a little bit of flagging to mark it, but not a lot because we don't want predators to find our nest. And we track them. We go back once a week and we see how the nest is progressing.
They collect a few eggs to determine the mercury content and to get a close look at how the embryo is forming. They check the bill and the other appendages and confirm their age approximations before sending it off for mercury analysis. As the chicks hatch, the team's work becomes a bit more exciting and difficult. Here they are collecting Forster's tern chicks, many of whom are close to leaving the nest for good.
habitat. 150. Wait.
So the study works with 3 species mainly. It's the forester's terns and the American avocets and the black-necked stilts. These are the forester's terns. So we're basically nest monitoring, finding out if mercury is affecting their nest success.
They are fitted with an identifying leg band and measured. Feather samples are taken to test for mercury, and then the young birds are released. These terns are fish eaters. The fish in their diet are also collected and tested for mercury.
Oh, that's interesting.
On the mudsuckers, they're extremely slippery. There's no scaling that you can feel with your hands, and their eyes are a little further apart than the gobies, which you can see are right on the top of its head.
Details on contamination throughout the food web are crucial to understanding the condition of the evolving habitat. The scientists are working to learn how an exploding gull population is impacting other birds in the area. The picture is not good. They have placed radios for tracking on 62 gulls. Each day they use telemetry to locate the birds. A fixed tracking station in the gull colony records when the wired gulls enter and leave.
We've ringed the South Bay in garbage dumps, so we've created an artificially high population of California gulls, but we're thinking a study will show what they do when they have chicks to feed, because they change to more local, more natural food sources, so the predation rate on the native populations, which are already being stressed by habitat loss in the area and numerous other stressors, now on top of that we've added this incredible predator that's going in, and we found that last year 70% of the avocet chicks in a neighboring pond ended up here, and only one of them lasted 5 days, the rest were gone within 2.
In addition to tracking the gulls, the team is using laser triggering nest cameras to monitor the nests of stilts and avocets. Each time a parent bird or a predator approaches the nest, a short segment of video is recorded. The scientists visit each nest camera bi-weekly, removing memory cards with recorded video and replacing batteries. Images from the cameras reveal a wide range of animals feeding on the eggs and young. It's gulls, skunks, raccoons, ravens, foxes, and more. Under these conditions, prospects for the native nesting birds, including stilts, avocets, and terns, are not great.
As we restore the areas, the gulls have come in, making it a little bit more difficult to predict the response of the birds we want. So the migratory shorebirds may be able to breed in this area as they have in the past, or they may be consumed by the gulls who actually come in and raid their nests and have effects on the young chicks that are bred in this area.
Just as the nest study of shorebirds and terns led to the revelation that gulls are a growing problem, the wide variety of science underway here provides crucial input on choices, questions, and uncertainties.
What we need to achieve, though, is a whole landscape level restoration, the right mix of habitats. They have values now. What are those values? What are the trade-offs? And because you're working and manipulating with so much of the system, you really need to have predictive models to tell you what will happen, and then you need to go out and ground truth those models for water movement and hydrology, salt, sediment, and the response of wildlife.
We've already seen numerous changes in the system as we've just replumbed the ponds to stabilize them so we can go forward with our restoration. But when we look out 50 years or so, we will have restored thousands of acres of tidal marsh here in the South Bay, so we'll have recovery, I believe, of the California clap rail and the salt marsh harvest mouse. We're also going to have a vibrant set of wildlife out in the old pond area. They won't be ponds anymore. It will now be really a wildlife refuge that will also have a number of trails getting into it so that people can actually access that and experience that, which is so critical here in the urbanized Bay Area. At the same time, we also will make sure that we build in flood protection as well for Silicon Valley. So those three things together, a vibrant natural system out there that people can get to and yet doesn't pose a threat to them in terms of flooding.
The sudden availability of these salt ponds is really a great moment in Bay Area history, a reversal of the trend of eliminating wetland habitat. As the understanding of the overall system evolves, challenges and uncertainties are inevitable. Science is there to provide some practical clarity to the process. If early results are any indication, quality of life in the Bay Area will only get better as the salt ponds transform into more natural habitat.
This restoration is the largest restoration in an urban environment ever undertaken. And so it's been very exciting because the knowledge on how to restore a salt pond to tidal wetland or as a managed bird pond, these questions are really unanswered as of yet.
We're really kind of stepping into new ground in restoration. And that is that restoration activities like these haven't occurred widely in the past, so we're kind of learning as we go. But the more we kind of ground it in basic sciences and understanding, providing information that helps to guide the decisions, the more likely the decisions will be the correct ones.
It's the interaction of the hydrology, the chemistry, and the ecology that's really driving a lot of the resource management issues out here, and what the Fish and Wildlife Service and the State Coastal Conservancy need to know to best manage this restoration and achieve their project objectives.
The fact is that an early investment of science